So synchronous motors, synchronous motors. Here we're discussing about the effect of excitation. What are the objectives? Yeah, effect of excitation on armature current and power. Here, the effect of excitation on armature current and power factor under normal excitation, under excitation, and over excitation. So now, here effect of excitation when synchronous motor is synchronous motor load is kept constant. That means load here the load is constant. There is no change in load variations. So that means power is also constant. Here the input power drawn by the motor will remain constant. So here the what is the power here? Power is equal to root 3 VL IL cos phi, that is constant. Since the applied voltage V and input power are constant, I cos pi is the active component of current is also constant for constant load. I cos pi is the here I cos pi is the active component of current, so it is constant for the constant load. If the load is varying, I cos pi also varying these quantities. Now next, here when the excitation is changed, the magnitude of induced EMF EB changes. So when excitation is changed, so DC excitation is changed, the magnitude of induced EMF will be changed. That is EB is changed. Now the load angle alpha is also constant for a constant load. Why? The load is constant. Now let ER is the ER is resultant voltage. It is between V and EB. And between means the resultant voltage between the voltage and that means supply voltage and back EMF. That is IAZS. So ER is equal to IAZS. So the theta is internal angle. Theta is internal angle, and that is the between ER and IA. ER and IA. So now theta is equal to the internal angle or impedance angle, that is equal to tan inverse x by RA. Theta is equal to tan inverse x by RA. Now IA is armature current. IA is armature current, and the Theta is power factor angle between voltage and armature current. In case 1, in case 1, the excitation is adjusted in such a way that AB is equal to V. That means normal excitation. AB is equal to V means normal excitation. Here, see this one. It is shown figure the IA lags V by an angle pi degrees. This is the voltage. It's showing the along the y-axis. That is so excitation and normal excitation along the y-axis, and here this arrow is showing the current I, and this the V and I is nothing but that is phase angle pi. That is pi. Now here this is the back EMF voltage, that is EB, and that is it slides with the some angle alpha, that is called a load angle. Now the resultant voltage between EB and V, which gives the ER, here by parallelogram method, by resultant vector diagram, we can get the ER. This is the ER resultant voltage. Between ER and I is nothing but theta, that is theta, that is called internal angle or impedance angle. Here in general EB is equal to V. That means the magnitude of back EMF is equal to the supply voltage. Before case, see, observe this one very careful. Under normal excitation, EB is equal to V. IA is lagging with voltage. IA is lagging. That means I is behind of that of voltage V with pi angle. This is synchronous motor, and then here the condition is EB is equal to V, and then go for case 2. In case 2, when the excitation is reduced in such a way that the back EMF is less than supply voltage, that means here the excitation is reduced. Now the motor is said to be under excited. The motor is said to be under excited. The resultant ER advanced in clockwise direction and as an angle theta constant. Here IA is also moves in clockwise direction. Shown figure, the angle pi is increased and power factor is decreased. To maintain IA cos pi constant, IA is increased. Therefore, for lower values of excitation, IA increases and power factor is lagging in nature. See here, Observe this diagram. AB is AB is less than A. So observe this one previous cases. This diagram of effect of excitation. This AB is equal to B. Observe this one. Observe this one. In case 3, when excitation is increased in such a way that AB greater than B. So here the motor is said to be over excited. The resultant ER is moved in anticlockwise direction. Resultant ER is moved in anticlockwise direction. So see here, observe the angle theta is constant and IA is also moves in anticlockwise direction. IA leads voltage by an angle pi. Shown figure, see the angle pi is increased and power factor is decreased. And to maintain IA cos pi constant, IA is increased then pi, therefore lower value of excitation IA increases and power factor leading in nature. Here this is the phasor diagram for over excitation. Here IA is moved to anticlockwise direction. In a similar way, the ER also moving in the anticlockwise direction. So for unity power factor, AB is slightly greater than B. Now, this is shown in figure. The excitation for which the power factor of the motor is unity is called as normal excitation. Here, then IA is in phase with V, as showing phasor diagram. Pi is equal to 0, and then here only theta will appear. So ER and I, V and I and EB, here EB is slightly greater than B condition. This is the case 4. Now in these all cases, the effect of excitation, see observe this one. When in the first case, observe this all, what is the difference between these all phasor diagrams in different cases? Observe this one. AB is equal to B. Figure A. the current in lagging with voltage supply voltage by angle of pi degrees, and here EB less than V under excitation, so pi value is more, so here I is lagging with the voltage V, the angle is pi, and here EB is greater than V, and the current direction is to anti-clockwise, and the here also anti-clockwise. Here the current is leading, and EB slightly greater than V. So here V and I are in phase. This is the effect of excitation of different phasor diagrams for different excitations. The salient features, some important points stand out clearly from the above discussion. So here the magnitude of armature current is varies with excitation. The current has large value both for low and high value of excitations are very important. The current has large value for both low and high value of excitations, and in between it has a minimum value corresponding to a certain excitation. Next, for the same input, armature current varies over wide range and causes the power factor also to vary accordingly. Whenever over excited, the motor runs with leading power factor, and with lagging power factor when under excited. The power factor is unity. The power factor is unity for approximately under normal excitation, and power factor is decreased either increasing or decreasing in the excitation. Now armature current is increased with respect to decrease in power factor. So here, we discussed effect of excitation on nature, armature current and power factor under normal excitation, under excitation and over excitation. Thank you.